morning, good afternoon, or good evening, whenever you're viewing this. Hi, I'm Dr. Tom Brum. I'm a faculty member here in the Department of Agricultural and Biosystems Engineering. And today we're here to look at what we call the Grain Teaching Lab. It's 4323 Sukup Hall up on the 4th floor. And I want to talk to you a little bit about if you take some of the classes that are in this lab, what you're going to do and some of the things that you'll experience. So my area of study is post-harvest technology. So everything that happens to the crop and now biomass after it leaves the field. For ag engineers and biological systems engineers, the course that you would likely take that you would be in here is ABE 469, and that's with Dr. Rosentrader. The course that I've taught in this room is TSM 322, which is kind of the TSM version of the same thing. The other course that I teach that you might have is ABE 325 Biorenewable Systems. So we talk about biofuels and all of that. And it's kind of connected, at least here in Iowa, to this yellow stuff that we seem to have a lot of. So one of the things that I'm doing right now, I'm standing in front of, if you believe it or not, it's a grain bin. It's a simulation of a mini grain bin. And in Iowa, half of the corn that we harvest gets stored on farm in a grain bin. So that means we have to take care of the quality and condition of that, both drying it and then in storage to be able to keep it in condition. So this is a little experimental operation that we use to measure airflow through a grain bin and how that varies depending on the properties of the corn, all sorts of things like that. So what we're trying to do is give you practical hands-on experience when we in taking some of the data that we use as engineers to design these kind of systems to store grain. In addition, there's a very large grain industry in this country. So drive across Iowa, you see grain bins, you see elevators, you see rail cars moving grain. It's a huge part of our state's economy, in the economy of the United States, frankly. And so there's a lot of technology that goes into that industry, and you get to some of the hands-on here in this laboratory space. So back behind me, you see moisture meters. So the value of the grain is in part determined by its moisture content, because if it's too wet, you get docked. If it's too dry, you miss an opportunity to sell water as grain. So there's a lot of technology in these machines, even though at the user level, you just pour it in and push a button. There's a lot of stuff going on behind the scenes, and so we have laboratories where you go in and you work with all these different kind of moisture meters to understand the technology. We do aeration of grain. We do fan sizing and selecting. We do grain grading. Gosh, what else? System design, right? So just like any manufacturing system, the storage and handling system on a farm level and an elevator needs to be sized properly and use the right technology. Because it's a lot of hands-on stuff that correlates directly to what's going on in the industry. Thanks for your time, and have a great day.
Today we're in Sukup 2207. I'm Christopher Murphy. I'm a program specialist here at Iowa State University for the ABE department. I've been with the university for 8 years, teaching the precision farming labs in the fall semester, and along with Dr. Dar, who teaches the actual TSM 433 lecture part of the course. In the fall, I work with that and also help with research projects for Dr. Dar. In the spring and the summer, I move to more of the research side for the projects that we're working with. So anything dealing with precision ag or UAV technology is technically what I work with. This class goes over, for the TSM 433 class in the fall that we teach, we go through the basics of GPS technology. So we actually have, in the classroom, we actually have a GPS repeater that is bringing live GPS strings into, or data into the classroom. So students can get a feel of what NEMA strings are and how that gets read into each receiver. And then we go through SMS technology. So SMS is Ag Leader Spatial Mapping Software. So we go through 8 weeks of going through different data sets, so whether it's harvest data or planting data. We also, if you can kind of see on the computer screen here, I actually got a 3D view of one of the fields with soil sampling data for organic matter. So we actually bring in elevation data, and we'll do a terrain analysis, and it will show us the slope in the field so students can see how yield is affected due to slope in the field. Once they go through the 8 weeks, they will build their own planting prescription. And with Ag Leaders technology, we can actually, with their in-command displays, we can set up a simulator, and they can go through and set up a planter. And while they set up the planter, they can load their prescription that they created in class and actually plant the field within the display. Once the field is created and planted, they can export that data and bring that back into their software to analyze that data set. It just gives them a live feed of using the display, setting it up, and then actually exporting and importing data in and out of a display to kind of get a feel of what that is like for a farmer or a producer.
I'm Tim Shepard. I'm an associate teaching professor here in the Department of Agricultural and Biosystems Engineering. As an associate teaching professor, my primary responsibilities are to lead students in both our technology and engineering curriculums. This semester and most, I teach ABE 363, which is applied electricity. So we learn all about how to control power systems for motors, loads, analyze different electrical circuits, very hands-on type experiences. The lab we're in today is Sukup 3224, which is our instrumentation lab. And some of our 363 lab gets to be in here where we work on computer simulations for controls with PLCs and introduce them to programs like Multisim and LabVIEW that allow students to explore circuits and control systems virtually. So as you look around this room, there's a lot of fun things. In ABE 404, 504, we learn about instrumentation, sensors, control systems, and the students spend the majority of the semester learning about how to design circuits that sense our environment and make control decisions. At the end of the semester, every student is working on a group project where they build a prototype system and watch its function. Most of the projects that are assigned in this class are selected by the students, and it focuses on areas of interest for them. So I try to pair students with projects that they might see in the future. All right. So over here is a heritage project from a capstone instrumentation project where a group built a model of an automatic baler. All right. And so one of the groups this semester is going through, we're about 2 weeks out. So in about a week, this thing better be running. But it utilizes paper towels to simulate a forage that is going to be rolled into a bale, and it processes this whole system automatically where it actually reels up paper towels. It senses when that reel is full. There's different automation processes that indicate the status of that system, and eventually it kicks out a bale. So that's a fun project. As we move into what lab stations look like, we typically work in pairs, but students are also allowed to work virtually at home. I've been using Zoom in the classroom for 5 years. So I broadcast my station onto their computer, and they can work down here practicing on programming, see images and demonstrations. We have access to signals that I can send out to every station so they can pick up things like voltage and current signals, pulse signals. We have oscilloscopes that allow students to see the real-time signal. This was a project that was built many, many years ago when I was an undergraduate. It's been utilized in this lab. And one or more of those students actually took that and created a commercial system called See and Spray. All right? So as they go through and look at minimizing the impact of herbicide applications, one of the things is only spraying where a weed is detected. So we're learning about the fundamental basic principles of how these systems work and operate, okay? All the way to looking at how might I monitor a bioreactor removing nitrogen at the edge of a field, okay? So how do we take samples out of that? How do we understand the flow rates? How do we measure water depth, flow rates, pH, nitrate levels, right? So our department has a very wide and broad breadth of students and student interests, and this class, ABE 404, provides them and you a great opportunity to explore and really have a lot of fun at the end of your college career.
My name is Li Tan. I joined the ABE department in 2004. Right now, I'm a professor in a focus area called Advanced Machinery Engineering and Manufacturing. So my responsibilities include both teaching and research. My research program is mainly in the area of automation and robotics. I work on federal and state-funded projects in areas of agricultural automation. This room is the teaching lab for TSM 465 automation systems. Here, as you can see, we have our equipment placed in this room. So around the room we have stations. We call the program logic controller working stations. And then in the middle of the room we have some robotic arms. We call them robotic stations. So students in this class, they work very closely with the hardware, the tools for both the hardware tools and also the software tools to understand and really to master the skills required for the automation of the process control. So this is our robotic training station. We customize this station so students can work very closely with the operation of the robotics, understand the fundamental principles of how to teach the robot, how to program the robot. For example, they have just developed this program to transport the parts. So this program a group of students just developed. I'm going to give you a very quick demo. So as you can tell, the student would be able to really have a very precise definition of the waypoints and also to command the robot to execute certain actions to grab the parts and then also to accelerate and deaccelerate at proper time during this transportation process. So here we are in front of a PLC training station. As you can see here on the desk, we have this white box we call the PLC trainer. So again, PLC stands for Program Logic Controllers, which is most widely used controller for industrial automation. So here in this class, we have very in-depth full spectrum coverage of how PLC it should work and how you can come up with your solution for automation process control. For example, with this trainer, which is customized by our department, so students can really understand how they can interface with the inputs and outputs around this central control device, and then move on to the software so they can develop this software to see how the program is realizing their logic. So this simulator is called the Logix Pro, and inside this simulator we have a series of practices for students to go through. For example, what you see here on the screen is a simulation program called Bottleline Simulation. This is more toward the end of the semester where we start to coach students to really individually to be able to accomplish a project which really has certain complexity. So I also work very closely with both graduate students and undergraduate students in this department. For example, often I hire undergrad students to help my research projects and also my teaching projects.
It's Mahari Takeste. I'm an assistant professor at the Ag and Biosystems Engineering, Iowa State, Ames, Iowa. So in my group, I do research on soil-crop-machine interaction, both for modeling and testing. I also teach undergraduate and graduate level class on soil-crop-machine performance, simulation, and modeling. There are two courses. So the main thing that I do with my students, both from particulate level is to bring particles which vary in their size and shape, their behavior, all the way to a simple laboratory measurements to quantify their behaviors or the performance of tools, and scale it up to an indoor facility that over the last almost 2 years and a half that I established with my colleagues. And it's a leading institution. It's going to be a leading center of excellence for soil machine dynamics laboratory. It's unique. It's the only one that has this scale size in North America, academic institutions. So students will go through both the research side for undergraduate and teaching, from learning about the particles to laboratory measurements, which we do it here at 3216 Soil Crop Mechanics Lab, and transition it to a scaled level, quantifying the performance of tire forces on a deformable soils, planter performance on a different compaction level measure prepared soil, which is our artificial soil, to the performance of tillage wear, and bring that to a laboratory. You can see here undergraduate and graduate students doing some 3D scanning of tools and bring them into a simulation. So we cover particles, simple tools, full scale or semi-scale level, and then bring it to simulation. I thank you very much.
I am Dr. Stuart Burrell, and I'm a full professor in the Ag and Biosystems department. My main responsibilities are teaching and research, and in terms of teaching, I teach the tractor power courses both to engineering students and to ag system technology students, and a lot of my research is involved in partially in sensor development and in combines and tractive efficiency of tractors. So this lab is part of the lab that we use for the tractor power courses, and a lot of the work that is done here is just to get the students familiar with engines and the components in the engines. And these engines are actually taken apart every semester and then put back together and made sure that they are back in running conditions. So this is the engine dynamometer controller, and it operates essentially as an electric generator and it changes the load on the engine. So I can set the engine speed I want the engine to run at, and then the controller will control the current going to the coils in the dyno and change the torque to for the engine to reach the speed. So I'm just going to set the speed roughly 50 RPM below what it is running right now. So we're going to go to 2200, set the speed, then I engage that speed, and you notice it's increased the load, and the torque has increased to 95 Newton meters, and that is at 2000. I'm going to go down another 100 RPM again. And when I hit this button is when the dyno controller will ramp up to the new load. So this is the powered machinery high bay, and the reason we have this very large space with very tall internal dimensions is we can bring any type of machine in here. We can get any combine that we can come in, or any tractor, bring it in here, and then have that as part of a lab for students. So this is really just movable space that we can utilize, bringing machinery in to demonstrate to the different classes. And this class is used for a number of courses: the tractor power course, the ag machinery course, and also sometimes in the hydraulics course. So the other two pieces of equipment that we're developing over the last 2 years is a very large vehicle dynamometer out at the agricultural research farm. And essentially that is a machine that we will be able to test tractors on from up to 650 kilowatts. This is just a single tire tester. So in this case, we have a belt that can, again, put a load on a single tire where the tire could be driving the belt or the belt could be driving the tire. And in addition to just teaching in these areas, at times we will also employ both graduate students and undergraduate students on our research projects. For an undergraduate student, if you get involved in a research project fairly early on, you start getting very good industry connections because much of our research is sponsored by industry. Then also it gives you an opportunity both to meet faculty and have a better relationship with the faculty who are controlling that research, and also meet industry representatives. And quite often that will lead to offers for internships and later on jobs.
Hi, I'm Brian Stewart. I'm Professor of Agricultural and Biosystems Engineering here at Iowa State, and I am in the Machinery Systems area. And this is the Danfoss Fluid Power Teaching Laboratory, which was funded and supported by Danfoss as well as a lot of other industries in the area. And it's just an example of the hands-on types of educational opportunities that we have here at Iowa State. What's behind me here is, this is a fluid power trainer, which enables students to connect up circuits and troubleshoot circuits and also collect data with the data acquisition system and sensors. And it's really the types of equipment that you'd find in the field, so it's actually real equipment that way. The classes that use this lab are primarily ABE ME 413, which is Fluid Power Engineering, and then also the TSM class, TSM 337, which is the Fluid Power Systems Technology class. So I hire undergrads occasionally when I have projects. We often do technical evaluation types of projects with industry, and I've done some in the hydraulics area. We're doing others in machinery testing types of opportunities out at the research farm. We're building up some lab facilities there, and so there are opportunities for students to get involved. I often do first-year honors projects, which is usually in the spring semester, and students will work on some research with hydraulics. This is the Danfoss Mechatronics and Agricultural Sensings Lab, and it's an area where we do sensor development and other research projects. And what's behind me is a project where we're monitoring the cleanliness of hydraulic fluid and looking at new ways to filter particle contaminants out of the fluid. Okay, this is the Vehicle Power Systems Lab, and you may have seen part of this in another video. Over to my right, my far right, is the engine dyno, and but this dyno here that I'm working with is a hydrostatic transmission dyno. In the Fluid Power Engineering class, we do a lab down here where students come. We take measurements on the hydrostatic transmission and help students understand the operation of that. Okay, another opportunity for students to get involved in is the Fluid Power Club, which we started last year. It gives students an opportunity to make connections with the fluid power industry. And so when we say fluid power, we mean both hydraulics and pneumatics. We focus a little bit more on hydraulics here because we work with agricultural machinery, but pneumatics is another important part of that industry. Part of the club and part of that whole organization that supports fluid power, the National Fluid Power Association, is a Fluid Power Vehicle Challenge. And if you can see here, we've got a couple of bikes here that we're building, and part of that challenge is to build a bike or a trike, has to be human powered, that uses hydraulics to propel the bike.
My name is Dr. Brett Ramirez. I'm an assistant professor in agricultural and biosystems engineering. I oversee labs 4218, 3215, and 3211 here in Sukup Hall. All these 3 labs support our research, extension, and teaching mission as part of the Animal Production Systems Engineering program. There's a variety of topics covered there, but at the core is all related to environmental control for animals. There are numerous opportunities for students to be involved in the labs. A lot of what you see here has all been constructed by students. They get involved as undergraduate research assistants and work along with our graduate students to create applied research and other research projects related to animal production systems. The system behind me here is what we use in our classes on teaching controlled environments for animals. Here we have a modern control system for controlling the ventilation. We also have a ceiling inlet for fresh air distribution and a typical ventilation fan for a swine facility. And here we can demonstrate pressure curves so students can relate airflow to static pressure, which is critical driver of ventilation. We also have a fans unit for measuring airflow. This device is commonly used in research for measuring airflow, to do fan performance and estimating air emissions from animal production systems. Another project we have currently going on is studying the effect of temperature, humidity, and airspeed over drying poultry manure. This is a problem because it can get too dusty or it can create too much ammonia. So this chamber here is built by one of our students and has laid out different levels to vary the environmental conditions across the manure plates. One of our recent research projects has been involved in exploring new microclimates for piglets. So what we have here is some instrumentation we've developed in a new semi-enclosed heated microclimate that kind of keeps the pigs draft-free and warm. We've also been experimenting with putting UV light to help synthesize vitamin D in the piglets.
Okay, so this is ABE Student Innovations Center. So in this room here is located in 1215 and 1209. Those 2 rooms combined together will make the ABE Student Innovations Lab. So this one right here is our water jet. When a student come in, or group of students have a need for something to be cut, and as you can see that the material that we can cut is very thick. We can go on to inch and a half to 2 inch. So this is the part that we just cut out. With the water jet, we have the potential to make a lot of parts for very quick, and it can be very precise within I think 40 of 1,000. So. And it can be a very complicated pattern for as long as we have a 2-dimensional drawing, we can do that. And we have no capacity to cut at an angle. Everything has to come straight. Engineering also provides some funding for us to hire probably 2 to 3 students that mostly will spend the time doing the cutting here.
Hello students. First of all, I want to say that we are socially distancing so that you can hear my voice more clearly. I am Michelle Supier, a professor in the Department of Agricultural and Biosystems Engineering, and I have both a teaching and research appointment. And today I'm going to show you our water quality research labs, which are on the 4th floor of Sukup Hall, and then I'll also be showing you our hydrology lab, which is in the basement of Sukup Hall. I have both a teaching and research appointment. The courses that I teach are primarily senior level or graduate level courses that our land and water students take. So for example, in spring of 2021, I'll be teaching the non-point pollution and control course, which many of our land and water students take, and also grad students may take it. And then in the fall, I will be teaching the watershed modeling course, which looks at different models or tools that can be used to predict the impacts of agricultural pollutants on downstream water quality. I often in the past teach the sophomore design class, which is is sometimes a really nice hands-on experience and walks students through the engineering design process. Unfortunately, I won't be involved with that course this next semester. My research appointment is looking at the impacts of agriculture also on water quality, and so really we focus on designing different conservation practices that can be implemented either in the field or at the edge of field to try and reduce the movement of pollutants from agricultural spaces down to downstream waters. Okay. So now we are in the basement of Sukup Hall in the bus hydrology lab. After we moved into this space in 2014, we worked with the University of Iowa to design this flume that you see behind me. So this is essentially a recirculating water system, a model of a river. We designed this flume to meet a range of different types of conditions. So it can go full force, over 9,000 cubic feet per second. So it looks like a river that someone in a civil engineering might be interested in studying. But we also have the ability to ramp that down to really low flow conditions so that you can barely see the flow, so it looks like sheet flow coming off of a parking lot. And so the range of flow conditions allow this to be a really versatile tool that can be used by researchers across campus. And then we also use this in the senior level land and water course, ABE 432, non-point pollution and control. Then we also use this flume for a lot of different research projects. Right now you can see the grass that's present in the flume. That's actually a prairie strip which was extracted for one of our studies, where we are looking at the impact of prairie strips on mitigating antimicrobial resistant bacteria. This lab can also be used for some other studies such as calibration experiments, so we can calibrate different instruments that are used to measure flow out in the field. We're also calibrating some systems that are used for agri-drain, so to measure or control flow into conservation practices such as wood chip bioreactors. So this is a really nice opportunity to have a controlled and known flow and to be able to work with a lot of different types of agricultural systems.
Hi, I'm Dr. Bob McNall. I'm a staff engineer here in the ABE department and also adjunct faculty. I lead research around machinery automation and data analytics and crop engaging sensors for ag machinery. We also have a focus kind of on developing technology and getting that into a production ready solution. So working on developing technology and getting that ready for commercialization. So we work heavily with industry in terms of developing R&D based technologies and then finding ways to accelerate that and help get it basically into producers' hands. I'm going to talk to you today about our class ABE 410-510, which is electrical system integration for ag machinery and production systems. And this class is co-taught with Dr. Matt Darr. And Dr. Matt Darr teaches the front half of the course, which focuses on CAN bus communication and provides a background on CAN bus communication, which is kind of the standard for ag communication on the vehicle between different controllers on the vehicle and the automation systems. And then the second half of the course is a focus on actually kind of putting that into more heavy practice. And so in the class we use what we have right here to my left is one of our trainers that is equipped with a embedded controller, which would be similar to what's used in the ag industry. This is actually an automotive industry kind of based development tool, but is also directly used in the ag industry. All right, so just a quick background on this board, kind of what we're seeing here. Number one is there are two CAN buses on here. There's a bus down here. It's the twisted yellow and green pair, and this runs across the bottom. That ties this controller, and this controller together. So when I say controllers, the only thing that really connects these three together is this yellow and green pair. So that allows communication between these three just through those two wires as part of the CAN bus. And what we're doing is we're actually controlling these functions so that the two actuators, there's two LEDs here controlled off of this. These switches are inputs into this, as well as this controller controls the motor here on this side. So the joystick is used to tell the controller what we want it to do. So it's interpreting our button presses and the position of the joystick. So the actuators actually move independently based on the two buttons, top and bottom, and then the joystick position controls the actual motor speed.
And one thing you'll notice is we're actually outputting a J1939 CAN message that is engine speed, so we're emulating that we're an engine, and this shows up on the display page on the ISOBUS display. So as I push this joystick forward, you'll notice the engine speed shows up and increases. We can load that up. And we also go through some control application logic in the class. So we actually have what we call like a little mini dyno on our electric motor where we can load this with a rheostat. So you can go through the process of how do I maintain a control speed on a motor as part of the logic process that we want to teach in this class.